Welcome to What Physicists Do. I have a few announcements. Tomorrow at noon, there is a Society of Physics Students meeting. Thursday, starting this week, in Darwin 37, there'll be weekly meetings for all the students that are doing capstone projects, leading up to our grand finale on Friday, May 9th, the day before graduation. And
is that Thursdays?
that's going to be Thursdays. It's in Darwin 37, starting this week.
Now, and I discussed that we added Thursdays to beef up our existing.
Right, but I think we still have them on alternate Tuesdays.
We still have them
too.
on alternate Tuesdays.
Yeah, so you can even those ones. So yes, you have to, all you seniors that are doing your capstone projects, time to get serious now. Public viewing night this Friday from 9 to 11 out of the observatory. And next week's talk is going to be by Nicholas Baruda, What Did One Physicist Do? The Many Facets of a Physics Career. This week I'm extremely happy to welcome our third of our official women in science speakers for Women's History Month, Dr. Lydia Sohn. She's from UC Berkeley. She got a bachelor's degree from Harvard or Radcliffe in chemistry and physics. She then got a master's degree in Harvard in physics and her PhD from Harvard in physics. She's done postdocs in the Netherlands and AT&T Bell Labs. She went off and was an assistant professor in physics at Princeton, and then she came to UC Berkeley, strangely enough, in the mechanical engineering department. And she's going to explain to us why that makes some sense. She's an associate professor at UC Berkeley now, and also the faculty assistant to the vice chancellor for research. She is part of the bioengineering core group that works with UC San Francisco, and she's won many awards and has several patents. The talk today is Node-Pore Sensing, how a simple 4-terminal measurement can screen for cancer cells. So it's a biophysics talk, something we haven't had any of so far this semester. Please join me in welcoming Dr. Lydia.
Thank you so much for the nice introduction and for inviting me. Really pretty campus. Let's see if I can get this on. Okay. Well, I guess it is true. I'm in a very strange, I'm taking a different career path than many of my fellow physicists. Just to give you a little bit of background and how I've gone in various different directions. Actually, and you'll see I've actually come full circle in many ways. We'll just spend a few minutes. When I was an undergraduate at Harvard, I wanted to be pre-med. I got into med school, broke my mom's heart, and decided to stay in physics. Or at least I did. And then I actually got my PhD with Mike Tinkham and did superconductivity, in particular just induction arrays, and looking at phase locking and microwave properties of JJ arrays. Then kind of zinged off, went off to Holland for a postdoc, and then Bell Labs when it still existed. And then at Princeton, I decided to come back full circle and apply my physics know-how and measurement techniques to biology. And I've kind of been stuck in that mode, and I do hear every once in a while my mom saying, see, I told you so. So, you know, having a Korean mom, you know those I told you so. Anyway, so what I'd like to talk to you about is this project that we've been working on in my lab since actually my Princeton days. And it's an amazing device that really centered on what I had done as a graduate student in Tinkham's group at Harvard. And we're just now applying it to cells and to basically biology. And I warn you, I really kind of have crossed over into the bio regime, so I only have 2 equations. So just letting you know that. I'm a little defensive of the physics community because I know what you expect. There's no H bar. But anyway, well, I'd just like to sort of tell you we're now very much applied right now, but all the fundamentals are still the same. And I'm really interested in seeing how I can actually apply a lot of the technology that I used from grad school days, and that was a lot of microfabrication. And really just how can we detect disease, look at disease progression, and in particular cancer, and it's personal for me because my mom has lung cancer, and how do people respond to therapy. And there's really 3 modes that people, when they sort of look into like diagnosis and monitoring, there are 3 modes that or approaches that people can take. They can do sample prep, they can do screening, and they can do diagnosis and monitoring. And what I'll talk to you today is really how we do this 4-terminal measurement to do screening and diagnosis and monitoring. So with that, and I'll just tell you how I got into mechanical engineering at Berkeley. At the time, my department was looking for the unusual ME person. So I said that there was no one more unusual than myself. Never took an ME course, so it was an interesting experience. Getting used to the department and everybody. But let me just show you, this is actually a picture of our device. And it's it doesn't get more simple than this. Literally 4 electrodes, and then I have a microfluid channel which I'll show a close-up of. And with that, we can actually diagnose, we can actually monitor and look at cancer cells from leukemia to breast cancer and so forth. So what we do is something called resistive-pulse sensing. And it's a label-free method, and the way biologists usually do for screening cells is that all cells have proteins on their surfaces called surface markers, and the protein markers really identify the cells in many ways. And so what we do is we're trying to identify those surface markers. But the way we do it is really very simple. We do a 4-terminal measurement. What we have is just literally a single microfluidic channel. Okay, and this is back in the day, back a long time ago in 2008. But what you see here is this is the actual picture of our microfluid channel, and this is a schematic, a side view. And what it's made out of is just PDMS, polydimethylsiloxane. So for those of you who aren't familiar with this material, it's nothing more than silicone rubber that you would pick up from the Home Depot. It's that RTP silicone rubber that you use to caulk up your bathroom tiles and so forth. And what we can do is we can make it lithographically, we can make a negative master of whatever we're trying to do. In this case, it would be the channel and these filters. And we pour the silicone rubber on top of our master, and we just cure it for a couple hours. And the beautiful thing is you can literally cut out your silicone rubber mold, which it becomes, and the master maintains it's very nice. You can use it over and over again. But you can take this mold and you can just plop it onto a glass substrate. In this glass substrate, what we have are predefined electrodes. We have current and we have voltage electrodes. And what we try to do is we actually dry cells with just pressure, just PSI, a few PSI. We dry cells from one end of the reservoir through this pore or channel. We call it pore just for historical reasons of how this project started, and then into the next reservoir. And when that happens, what we do is we end up measuring a current pulse. Okay? And it's strictly, again, the beautiful part, if you ever go into a bio-core lab, you see very sophisticated equipment and everything, lasers and so forth. We're running things off of a 15-volt battery. Or it's just strictly a DC measurement, but I'll show you how powerful it is. And what we're doing is we're measuring current. Okay? And with this current, we do a 4-terminal measurement because these cells exist in a cellular media, a buffer solution, which has salts and ions. And if you were to just do a 2-terminal measurement to measure the current across the channel, you would end up having these what they call interfacial resistance, where the current, a positive current electrode, would have all these negative ions surrounding it. And you end up measuring that resistance. And we're not interested in that. We're strictly interested in measuring the current across the channel. Okay? So that's why we do a 4-terminal measurement. And when there's nothing inside this pore or channel, we measure some constant current. And then as the cell passes through, you can think in very simple terms, it's displacing by volume a certain amount of conducting fluid. The cell is a dielectric or an insulator. And when that happens, that current drops, okay, displacing a certain amount of conducting fluid. And then as the cell all the way passes through into the next reservoir, then you see a rise in current because that channel once again fills up with conducting fluid. It's a very simplistic way of thinking of things, but what I'll show you is sort of the equations that govern why this all works. And it really comes down to looking at electric fields because this channel is nothing more than a wire. Okay? It's filled with fluid, it's conducting. Okay? And what you can do is you can go through Laplace's equation, you can look at the electric fields, the current density, and so forth. And what you end up, and these are my 2 equations, and then this is it, okay? What you can do is really look at 2 regimes. These were done by, calculated by Gregg and Steidley back in the 70s, and Dubois and Bean also in the 70s. And there are 2 regimes whereby you can have your channel, the effective diameter. Okay, this is assuming a cylinder. For my case, it's a rectangular form, but again, you can look at it as an effective diameter. And and the length of the channel, and then you can look at the size of the particle. In my case, it's a cell that passes through. And what you find is that you can predict the change in resistance, or that current pulse, the magnitude, based upon these two equations and then these two regimes. And you can see that they're highly nonlinear, they're dependent upon all these parameters and so forth. There's an F factor that's sort of done by going backwards and doing your measurements and so forth. And I think the F actually, when the Blah being created it, it really was the fudge factor. At least that's what I think it is. But in the end, this is some of the early data that we took about 10 years ago. This is how old this project's been, but I've gotten 3 PhD pieces. I'm going to get a 4th one out. I think it's just a device that keeps on giving. But here what we have is, this is normalized current. Okay? It's also the same as normalized resistance. Okay? And what we did is we had our device, and we were actually measuring colloids. And basically, the blue lines and the green lines correspond to those 2 different regimes, one either by Greg and Steinley or Dubois and Bean. And what you see is that we're very close, with our measurements, we're very close to what is predicted. So we actually have very high accuracy. And we were able to measure colloids in different sizes and do a variety of different immunoassays. But that was back a long time ago. And essentially what we now focus on in my group is actually not this pulse magnitude, looking at that changing current, normalized current as a cell passes through. What we're really interested in now is looking at pulse width. And that pulse width really corresponds to just the cell transit time. So in the end, what I'm going to show you is all data that corresponds to how fast does the cell pass through this channel at a given length. And this is how easy it is for us to look for those particular surface markers, those proteins that are on the surface. Essentially, what we're looking for are looking at protein interactions, the ligand and receptor, what's on the surface of the cell with a corresponding antibody that matches that protein on the surface of the cell. And what we do is we actually functionalize these channels, the glass substrate from which encloses, which the microfluidic channel encloses the substrate. And if we functionalize it with a specific antibody that can bind to the surface marker, it's a lock and key theme that we have going on, where there's only one type of protein, one type of antibody that can make the perfect match. And if there is a match, the cell, as it passes through our channel, will actually start to slow down. It's making these transient interactions, and it's just rolling, literally rolling through the channel on the substrate. And essentially what we see is that the cell slows down, and it has a certain current pulse width that we can measure. Okay? And then, because proteins, you have to have that control. In bio, it's all about control. So what we have here is we also have another channel that we functionalize with an isotype control. Proteins are sticky, so even if there's not a match between 2 proteins or a surface marker and an antibody, they will stick, and that's called essentially non-specific interaction. And we can measure that slight change of the cell slowing down a little bit. But if you compare the 2 transit times, they're not identical. They don't even come close, which is really surprising for us. And I'll explain why. And then if there's no interaction, there's nothing on the substrate surface, the cells just zip through. And with that, we're actually able to be very competitive with the standard. Yes?
So this is fascinating. Is it that you implant antibodies in the RTV type material? Sorry, I don't remember the acronym.
So actually we functionalize the substrate surface, the glass. We do a whole chemistry functionalization. We cyanate the surface, and we use various types of amines to actually bind the antibodies onto the substrate. But when we do our incubation, it's a really great question. When we actually incubate the antibodies to make that connection with the glass substrate, the antibodies do actually get absorbed by PDMS. It's a polymer, and so the antibodies will go into the nooks and crannies, so to speak, on the molecular side. And because it's a hydrophilic interaction, the antibodies are actually pointing in the right direction inside it. So we lucked out in many ways. Okay, so let me just show you proof of principle that this really does work. And this was done with these mouse cells that were all CD34 positive. CD34 is a particular marker for leukemia. And this is just raw data. So you can see how clean our data is. Normalized current versus time. You can even see the time scale which we're measuring. It is slow, but we don't need to measure much to actually say things are positive. This gives you the size of our pore or our channel. It's 15 by 15 by 800. and so forth. Here's the blank case where the cells are just passing through a channel that's not been functionalized. You can see that these current pulses, each pulse corresponds to a cell. They all vary in magnitude and size, and the reason being is that cells are just naturally vary in size. Okay? Here it is with, this is known as the IgG control, and this is just our control antibody. So this is where we're measuring non-specific interactions. And this is where we actually functionalize with the specific antibody, anti-CD34. And again, you can see the pulse magnitudes all vary, but you can also see slightly, if you're up close like me and know what to look for, you can actually see that these transit times are, pulse width is much narrower than the transit times here. But let me just show you what we've done. This is just looking at the blank channel and then looking at the pulse magnitudes. And going back to those equations that I showed you, what we did was we converted it to the size because we knew the size of the channel, we knew how long it was. We're just looking for that little d, what's the size of our particle. And this shows you the distribution of our cells in that population. And there is a natural variation in cell size. And this is 66 cells. Now this is really just showing a proof of principle that it does work. Okay, and so you can see here we're looking at the transit times or the pulse width. And for cells that are going through the blank channel or that would go through the control channel, you can see that there's a nice tight distribution. The cells are taking about, on average, about 6 milliseconds to pass through an 800 micron long pore. Okay? But what you see very, very, very nicely is that when the cells are passing through this anti-CD34, the specific antibody channel, they're taking much longer to pass through. And that shows us that, yes, indeed there is an interaction. There is a specific interaction, and the cells are just taking longer to pass through. It's like they're going through Velcro at that point when it goes through. In addition, what you see is that instead of this tight distribution that we saw with our blank and our control channel, actually now the variance is very, very wide. And what I'll show you in terms of, we can explain that by saying really that what we're doing is not only saying a yes or no, the cell has this marker or not, but in addition we can tell people, yeah, there's a high expression, there's many markers, specific markers on these set of cells versus these set of cells. So that's very nice. It sort of goes beyond what biologists would do, which is just tag the cells with a fluorescence marker and then look at fluorescence intensity. But let me just kind of going ahead of myself, but I just wanted to show you how we compare to the gold standard, what the bio people would use, and that's flow cytometry. So how many of you know what flow cytometry is? It's a few of you. Okay, so you do have a slide there. So flow cytometry is the standard, and I'll just show you how it's done. Again, what you would do in flow cytometry is you would actually take your cells and you would incubate it with a specific antibody. So in this case, it would be the anti-CD34. The anti-CD34 would actually have a fluorescence tag on it. Okay? And then what you do is you take your cells after you've incubated for a very long time, and that's key because we're going to revisit that towards some new data that I'll show you. But essentially, you pass these cells through a flow cytometer, and that flow cytometer has at least one laser, and the laser is shining light as the cells pass through, and it's going to try to excite those fluorophores, those tagged antibodies, if they've actually tacked onto the cell. And if it does, then you can actually sort out these cells, which ones are positive and have fluorescence, and you can actually sort out the cells that don't have the fluorescence. And that's how it's usually done in bio. The state of the art is you can actually measure about 18 markers simultaneously, which means you have 18 different fluorescence tags there. And what you do get into a lot of trouble because there's a lot of spectral emission overlap. And I'll show you how we've actually addressed that we can avoid that. With us, a 4-terminal measurement, a DC current measurement is all that we need. These things are very expensive, so it's really kind of nice that we have this very cheap system. But let me just show you how we do compared to that flow cytometry. It's a very sensitive thing. It's been going, this technique flow cytometry has been around since the 1950s. Okay. And essentially, what we did is we were looking at some cells that are positive for something called SCA1, which is a stem cell marker. And we're always doing a comparison. What is our control? What are those non-specific interactions? How long does it take for cells to pass through that non-specific interaction? channel versus what's going through the specific interaction channel. Are the cells actually slowing down? And so here's a sort of a distribution of cells that pass, stem cells that pass through the control channel versus through the specific antibody channel. And in the comparison, you can see that there are some cells that are shifted to the right that are taking much longer to pass through the channel. Those are the cells that are positive for SCA. Just for people who are curious about whether or not there's any correlation between cell size and the transit time of cells passing through, and what I'm showing you here is a scatter plot between cell size and transit time, and you can see that there's no correlation between the two, which was very nice and reassuring for us. Here's some flow cytometry data where we're just again looking at fluorescence after the cells have been tagged with SCA1 antibody that has been attached to a fluorescence tag, and you can see a shift to the right. There's some cells that are more brightly fluorescent in this FITC regime. Okay? But it takes a lot of math to actually go through this. We actually use something called false discovery rate. So I've learned a lot of statistics. And I wish I had taken statistics as an undergrad. So for undergrads, you should take statistics. Grad students, you should take statistics. But anyway, I really am learning a lot, which is nice. Essentially, we have excellent agreement in flow cytometry. We get 67.6% of the cells are positive for SCA1 versus flow cytometry. Doesn't get any closer than that, about, in terms of it's a direct match. Now, as I mentioned before, that when you go back and think about that broad distribution of cells that are positive for CD34, and I said that the variance is large because some cells have a high expression versus low expression, we actually want to show people that yes, we actually are measuring levels of gene expression, levels of these markers on the surface, how many there are. And so just taking a look at this distribution, here are these cells, and again, they're very well spread out in terms of transit time. These cells, we guessed, had high expression of SCA1. These have lower expression levels. Okay. Well, what we did was to actually show people that we were sensitive is we took cells that were all positive for SCA1, and we started to incubate them with antibody at different concentrations. And by incubating them with different concentrations of antibody, what we essentially were doing is we were blocking these sites, these surface markers, from actually being able to interact with the functionalized substrate surface. And with that, then it was really nice for us to show that if there were very little receptors that were blocked out by antibody, free-floating antibody in solution, these cells then essentially could interact. They had a lot of receptors that couldn't interact with the channel, and so they took much longer to pass through. Versus the same kind of cells, but now we've actually blocked almost all the receptors on the surface of the cell, and they can no longer interact with the functionalized antibody, and those they just pass right through the channel. So you see this very nice saturation curve, which is what we expected to see, and it was to show people in the end we're very sensitive to this level of gene expression, or these surface marker expression levels on the surface of the cell. And this is something that's sort of applicable to pharma industries where they want to develop drugs based upon concentrations of antibodies and surface markers. Now, for people who might be concerned is, well, as these cells pass through, they're transiently binding onto these, with these antibodies. And one of the things that we've noticed when we actually tag the cells with fluorescent markers and then measure them with flow cytometry is that we actually, because the cells are now bound, they have a surface marker that's bound to an antibody, we start to change things inside the cell. And it's not great, because if you're trying to sort of elucidate some kind of information, you've changed the cell, you've perturbed the system. So we want to show people that we're not actually activating, we're not perturbing the system, even though there's transient binding occurring. And it all has to do with time, the actual time that it takes for these antibodies and surface markers to interact. We're working on the millisecond regime. For other things with flow cytometry, we're working on hours in which cells are interacting with the antibody. And this sort of goes into a lot of detail, and there's a lot in this graph. But suffice to say, what we did was we looked for a particular marker that's on the surface of stem cells. It's called the notch surface marker. And when it's actually bound to an antibody, it immediately starts to change the cell. And it's actually very difficult to measure this notch marker through any means biologically, just because the cell immediately starts to change. So what we did was we ran our cells through and we looked for that notch. And you can see here we now, because we know that we are sensitive to the surface marker level, red here corresponds to high cells that have high expression, green is medium, and blue is low. But suffice to say, what's most important is that we look for sort of the pathway, this notch pathway that becomes activated in the cell once the notch is bound to its antibody. And essentially we showed that with our device, this is the channel with our control and our specific antibody channel, the amount of cells that are activated is the same as a controlled well in which we just took the cells and incubated with the control antibody, versus when we've actually incubated the cells with the specific antibody, free antibody. And it just shows people that we can actually, the cells are not activated, and more importantly, we can actually recover these cells for further analysis. It's a very detailed thing, but it just reassures a lot of people who are looking into these kinds of interactions that we're not changing the cell in any way. But overall, this label-free way of doing things, we're actually not, we literally just take cells from what we grow in our lab, and we just inject it into our device. We don't do any kind of incubation. It works extremely well. It's label-free. And it can be applied to different systems. We're working on cancer cells and we're working on stem cells. But at the end of the day, we have a problem with this method. And I'm going to show you sort of how it suddenly made this big change in the last 2 years of improving our method of measurement. And that is, we were always comparing a channel that was a control antibody channel versus a specific antibody channel. And we were always statistically comparing one set of cells with another set of cells. It was never the same set of cells. And so it was this, we had to do a lot of different kinds of corrections and so forth statistically to compare transit times and so forth. And it was just cumbersome. And in addition, it was also a case where we can only measure one specific marker at a time. And so a few years ago, when my graduate student Karthik thought, like, is there a way that we can do this better? Is there a way that we can do multi-marker screening? So it would be equivalent of taking cells and putting multiple antibodies on their surface that all glow at different colors and actually running it through flow cytometry. And for us to do that, we realized that we had to change everything about our device. It's still a microfluidic device, but now it's completely different, and I'll show you how. So, and this is where we've transitioned from calling it Resistive-Pulse Sensing to Node-Pore Sensing, or NPS. And so here's our straight channel, and when a cell passes through, we get this noisy curve, but essentially you get a single pulse for a cell passing through. But now, what we do is we actually change the geometry of the channel. We introduce these, it's small to see, and I have another picture better in the next slide, but essentially we introduce these nodes or widened areas within the channel. And when we do that, then the pulse, a single pulse that should be like this, is now subdivided. And it's subdivided by the number of nodes that we insert into our channel. And so forth. So here's another channel where we've inserted 11 nodes, and now the channel, it has many multiple, it has been subdivided by those 11 nodes. Here's one that's put into a Fibonacci series, and we see the Fibonacci series in our pulse. Why Fibonacci? Just because we can. It's always the joke in the lab. But why does this work? You know, again, remember when I said that, like, you can think of this as the cell passes through, it's a dielectric, it's an insulator, it's displacing a certain amount of conducting volume. So it's almost a volume to volume ratio of what you expect in terms of changing current that you should measure. But in this case, the best way to explain why we see how, or essentially how does it work that these nodes can actually subdivide the pulse, what you have to come down to is that go back to your electric field lines, your electric field density, go back to Maxwell's equations, the Laplace's equations, and what you realize is that the current density at the nodes is much less than the current density of the channel. Okay, the channel is more narrow. And at any instantaneous moment, you can see how that cell is sort of affecting the current density in this channel versus in the node. And with that, then you can see how the actual current pulse has been subdivided. And that becomes really nice because we have an amazing dynamic range. So essentially what we're doing is we're actually taking our channel and we're actually coding it so that what we'll see is a specific electronic pulse that we can measure, current pulse that we measure. It'll have a distinct electronic signature. So here is a case where we have actually a 4-node device. This is much nicer to actually see the nodes. Okay, it's 8 by 10 in cross-sectional area, and it's 500 microns long. And what you see is these are different sets of colloids that we've passed through the same exact channel. And even though our data is really noisy, and really should have been cleaned up a long time ago with a lot of electronics, but essentially what you see is it doesn't matter for us. All we're always looking for is a current pulse that has been subdivided spatially and temporally by these 4 nodes. And with that, even though we have something that's 50 nanometers, we can pick up these sort of subdivisions of that particular current pulse outside of the noise. And that really helps us. So in the end, if one were actually to take a channel, a straight channel, and try to measure something that's 50 nanometers, because of this volume to volume ratio that we have to measure, in a sense the channel would have to be down to 100 nanometers in order for us to actually pick out that current pulse out of the noise. Okay? For a 5 micron colloid, if you were to have this all in a mixture of these 50 nanometer colloids, essentially the 5 micron colloids would actually clog up the channel, obviously, with a 100 nanometer channel. If we were actually to just take this channel as its original size but remove the nodes, we would very clearly be able to measure these sets of colloids, but there's no way we could pick out a 50 nanometer colloid pulse out of the noise. So it's really nice that essentially what we're doing now is encoding our channel with spatial and temporal properties. And so I like to emphasize that with this Node-Pore sensing, it's really powerful because in the end, signal-to-noise ratios don't matter at all. And just to sort of show you, this is something that I always have to show people in engineering, but it's just showing people how sensitive we are. And we're at the order, if you look at just the volume of a particle with respect to the volume of the channel pore, we're down to 10 to the minus 9. And that's just something just to show people. What I'd really like to show you, which is really cool, and this is just a neat thing, is that you can actually do signal processing with these nodes. And this is something that we're really pursuing a lot right now in the lab, which is essentially we have this channel, and here we've encoded our channel with these nodes that are spaced differently, closer together here versus wider here. And what we've done just for a clean show of data, this is a colloid passing through, and what you see is that this entire current pulse is now subdivided so that it has a high frequency signal versus a low frequency signal, just based upon where these nodes are. Okay? And with that, then you can actually do an FFT, and instead of looking at transit times and current pulse, transit times and everything, you can just pick up all your pulses with an FFT. So you can actually know your answer a priori. So it's a really cute thing, and it turns out to be quite powerful. Now I just want to emphasize that, like how powerful this method is before I go into talking about cells again. But we've demonstrated that you can actually use this device as it is without any functionalization of antibodies by actually doing a real-world application. And that is, we've been able to detect and enumerate HIV in human plasma, and we've been able to detect and enumerate the HIV particles. The way HIV is detected is usually through your T cell numbers and particular markers on the T cell. With this, we're actually directly enumerating the HIV particle. It's hard to do biologically because the HIV particle is down to 100, 120 nanometers. So this is actually that 4-node device that I just showed you. And what we did was we took human plasma and we spiked it with a certain number of concentration of HIV particles. And what you see here is that this is noisy data, 10 nanometers per 10 milliseconds. Those are the units, or the whatever you call it, units. But essentially, human plasma has just junk in it. It has proteins, huge clotting things, and so forth. And we're able to measure fibrin particles or protein particles that are greater than 1 micron. And again, you see that 4 distinct subpulses of a single pulse. And then if you just look downstream, there's this funky noise, okay? And sometimes we even tell people, you could do an FFT, but because we're always just looking for a specific electronic signature, you can just put a low-pass filter on, And what you see is that this funky noise area actually is a pulse, and it's subdivided. You can see the 4 distinct subpulses. So then we know, oh, it's an HIV particle. The same thing applies that even though you have these nodes, you can actually still look at the current pulse magnitude. Okay? Instead, you have to use another fudge factor with that de Bois-Mean calculation of changing current or changing resistance. But essentially, you can determine size. And it's nice that everything sort of just backs up on each other. But here's sort of data that we see, and I'm sorry that this is very small, but know that the blue here corresponds to just plasma. Okay? And we see particles ranging anywhere from 250 all the way up to 1,200 microns. Okay? But here are 3 different cases, 3 different experiments where what we've done is we've added HIV into it. And we see that there are some particles that are about 200 nanometers or less, and those actually do correspond to the HIV. Okay? You can also just look at the volume of fluid that we've actually measured, backtrack with the number of copies of HIV that should have been in that volume that we measured, and we get the same number. We're counting every HIV particle, which is very nice. And this obviously has some real world implications on actually looking at people during therapy if they're HIV positive. So it's nice to show that people that, it's a valuable technique. You wouldn't be able to do this if you were to, use a single channel, which is really what flow cytometry also is. It's like you're taking an aperture and you're flowing cells through. With this case, everything would have gotten clogged by all the protein particles that are in plasma. You wouldn't be able to measure HIV, which is why people use this indirect method. Okay. So let me just go back to Node-Pore sensing with that introduction and how you can actually use it for multi-marker screening. And again, everything that we do is super simple. Okay? So this is how we now do it. Because we can subdivide or channel by these nodes, we can actually functionalize different sections in between the nodes with different antibodies. And then we can look at our single current pulse that's been subdivided by the nodes, and we can look at the transit times of these subpulses. If a cell is positive, for instance, this was positive for red antibody, the transit time of the cell passing through that would take longer versus these other 2. The green one, again, you would see that if current versus time, it takes longer to pass through the green antibody section versus all these others. And it turns out that, again, this is remarkably, it solves our problem, which is what I was talking about, that we always have to statistically compare one set of particle cells versus another cell in two different devices. But the other thing is now we can actually look at multiple markers on the surface of the cell for each different cell. So let me just show you how we fabricate the device. Super simple. Okay, we still do our standard lithography. We take our glass substrate, we pattern our electrodes, still 4-terminal measurement, current and voltage. And then we have a temporary PDMS slab that we've molded with multiple channels. And we basically position that temporary channel that it runs 90 degrees with respect to how the Node-Pore will actually sit. And we functionalize essentially those different sections in the different channels with different antibody. Pull off the channel, that temporary slab. We have these pattern stripes. Then we take our actual Node-Pore device, we pull out our Node-Pore, and then we actually position it on top of our channel. On top of our substrate, we clamp everything down, and this is actually a fluorescence image of antibodies that we functionalize, and these are the nodes right here, and then this is an actual node. Okay, so again, it's very simple, and then we just inject our cells. So I'll come around as to why we're actually looking at leukemia, but let me just show you what we've done. Here's where we've actually looked for 4 different markers per cell. And again, for us, it didn't matter because signal-to-noise ratios means nothing to us. We're always looking at current pulses that have a specific electronic signature. And here we've actually incorporated our specific antibody section right there, non-specific antibody right there. So we're comparing all the transit times for CD13, 14, blah, blah, to this transit time of the anti-IgG. Okay? And this is a typical pulse. We actually slow down the cells as they pass through so we can actually get a nice clean pulse. But you can see here, each section here corresponds to a cell first going through the CD13 section, the 14, and so forth. And you can see how much we've slowed down our measurement time and so forth. and this is current, changing current in nanoamps. Okay, you can say like, oh, you know, from the eye, it looks like they're all very closely spaced together. How can you actually look at the transit times and compare? You actually can, and with that, then you actually get really nice data. So this is something that my student had taken some data off of something called NB4 cells. And I'll talk about what the importance of these cells are at the end, and so I wanted to sort of explain what this data means. And essentially what we do is, each one of these boxes, dotted boxes, actually corresponds to a single cell, okay? And the dotted green line here corresponds to the average transit time of cells passing through that IgG control, okay? Cells that are, their transit time in the specific section of the channel, if they are greater than, the transit time is greater than that dotted green line, that means they're positive for the marker. Below, they're negative for the marker. And essentially what you see is for cell 1, it's positive for 13, 33, and 15, but negative for 14, and so forth. Now, how would this look if you were to do flow cytometry? Essentially, you would have a whole series of curves with respect to fluorescence. You would see some overlap because essentially you would have to dye these cells with different, with each cell would be incubated with different antibodies that have different fluorophores of different emission range and so forth, and it can get quite complicated. But this is our overall data for these set of cells. Okay? And these set of cells, I think we used like about 100 cells that we measured, and we were able to get how many percentage were 13 positive, 14 positive, and so forth. And this is giving you percentage NPS of our device. FACS is flow cytometry, and you can see that we have really amazing correspondence between the two. Okay, we actually have done a chi-square test to show that these two methods for these different markers are statistically indistinguishable if you set the p-value to 0.05. Our only problem right now is CD33, and I have an explanation as to why that is. But everything else, it's very nice to see. Another set of cells, essentially we do the same type of a measurement. And again, this is our comparison with percentages with our method versus flow cytometry or FACS. Again, everything is, the chi-square test again shows that the two methods are indistinguishable except for CD33. Now CD33 right now is a problem for us. And what we think is happening, again, all has to do with how much does the cell, how long does it have time to actually interact with the specific antibody. As I mentioned earlier, when you do flow cytometry, you're incubating these cells for a very long period of time, for a couple hours with antibodies that are in suspension. And so there's a lot of time for the antibody to actually make the interaction and to bind. Okay? Binding really takes on the order of minutes or so. For us, we're looking at these transient interactions on the order of essentially milliseconds. And so it may be the case that every antibody and protein, they all have different affinity binding constants. And so this one is a case where essentially the binding constant is not that strong. And so essentially we're not being able to pick up all the CD33 surface marker interactions with the functionalized antibody. That's what we think is the case. But just to make sure, and we still have to repeat this test, but we wanted to know, well, are we really sure that all the cells are actually interacting specifically or non-specifically with the antibodies? We're pretty sure that it does, because the cells do take a while to go from the reservoir and into the channel, so there's time for gravity to take place, and for essentially the cells to sediment to the bottom of the substrate. But just to make sure, what we did was we incorporated redundancy. So this was a really nice test for us. We actually also looked at two different set of cells. One was positive for a protein marker called HLA-DR, and the other one was positive for CD13. And it doesn't matter right now which one is which, but really the most important thing that I want to show you is that what we did was we repeated our pattern of antibodies on our device. So essentially we wanted to make sure that we were capturing all the cells interacting with the antibodies. And this is the kind of data that we got. And again, anything positive, anything greater than that green line above, the cells are positive for the marker. Anything below, it's negative. And I've highlighted two specific cases that are in purple with these purple stars. For cell 1, as the cell passed through, it turns out that in the first section, it was not positive for HLA-DR, because the dark blue is below the green line. But then, when it got into the second region right here, where it's going to interact with HLA-DR again, it actually turned out it was positive. It wasn't strongly interacting with that antibody. So with that, this is a case where the cell was positive for HLA-DR. Now you can argue that, well, it just took a long time for the cell actually to sink to the bottom and interact with the substrate surface. But here's a case where, in this case, in cell 9, it turned out that cell was positive for HLA-DR in the first section of the device, but negative in the second section. So with that, we know that some cells just don't interact very well with the antibodies, or there's all this cell mechanics going on, which we still need to sort of model and so forth. But essentially, we're able to sort of capture those false negatives. And essentially, in the end, that is the case that if you take all the cells and you do your sort of Venn diagram of which ones are positive and negative and so forth, we find that certain cells are 41% positive for HLA-DR, and then 49% are positive for the other marker. Flow cytometry, you almost get the identical number. So it's really nice to see that you can incorporate redundancy. And again, we have to work out the cell mechanics on really how do the cells interact, how are they binding and unbinding, what's really going on in the system. So let me just sort of take a step back. This is like all the data that we have right now, but as I said, I'm motivated because cancer has a big role in my family's life, but why are we focused on leukemia? And in many ways, the most amazing thing that we've learned by talking to oncologists in the area is that leukemia is really considered now a manageable disease, okay, versus colon cancer versus prostate versus breast cancer. It's now, at least in the United States, there are certain leukemias that you can actually tell a person you're cured. Otherwise, it's a manageable disease. But this is not the case for third world nations, or what they call low resource setting areas, or even middle income resource settings. Middle income would be your country hospitals, your community hospitals, where the flow cytometer, where various cytogenetic, various PCR type of machines are not available to do the diagnosis. And it's really astounding in this day and age where in the U.S. we consider leukemia a manageable or curable disease, that for childhood acute lymphoblastic leukemia, or ALL, it has a greater than 80% cure rate in industrialized nations. Okay? But it's less than 10% in developing countries. It's really quite remarkable. Okay? There's another disease that's called acute promyelolytic leukemia, or APL. And those were actually the cells that I was showing you in the previous graphs. But this was known as one of the deadliest type of leukemia. And really what happens is back about 10 years ago or more, patients would come into the ER, and I'll sort of describe what happens, but essentially, they would essentially bleed out and die before they were diagnosed with this particular type of leukemia. Now, we have nearly 100% remission rate. You can actually tell people you're cured of APL. But in countries such as Latin America, until recently, the mortality rate was greater than 50%. And this is where we actually think that our device can make a difference in these areas, whereas you would have to spend a lot of money and have a dedicated technician to do flow cytometry or genetic analysis. But here's our device. Anyone can use it. I've got undergrads, I've got high school students running our experiments. And essentially, you could actually have this done at the bedside. And you can make an impact on someone's life, and at least tell them maybe you need to go to a major city hospital, you need to go to a university hospital to get this checked out. But let me describe about APL, because I find this quite fascinating. Essentially, again, back 15 years ago or so, or even more, essentially a doctor had 48 hours to diagnose you for APL, okay? And the actual how it starts out, you can just suddenly start to develop, like a patient will suddenly feel like he has a fever, general malaise, and it has bleeding in the gums, for instance, right? And when all of us feel a little bit sick, do we really want to go to the ER? Do we want to go to the doctor? Everyone delays as much as possible. And this is where, in this disease, time matters. Patient then, when it really starts to feel bad, will finally go to the ER, but you know, any ER is at least a 5-hour wait. At least that's what my husband says. It's always 5 hours, right? And essentially, they'll take a CBC, you may show anemia, you have elevated white blood counts, low platelet counts, and so forth. But no one really knows, maybe you have an infection, or maybe you have anemia, and so forth. So there's time wasted again and again. Now, in the end, if you're lucky enough to have an oncologist on call or someone suspects it, they'll actually ask the pathology lab to do that flow cytometry to actually look for specific markers that correspond to APL. And if it comes back positive, then what they do is they give you a pill called Atra. It's essentially a vitamin A-based derived drug. And with that, essentially then the patient, it stops the patient from exhibiting and showing symptoms. And it stops the leukemia in its path and starts reversing everything. If you don't get to that stage where they actually can give you Atra, and within this 48-hour window, these patients will essentially die of bleeding out. They will bleed out. And you know, it's really an unfortunate situation a long time ago. And so, in the US, again, if you are near a university hospital or essentially a city hospital that has the facilities, has the pathology labs and so forth, then essentially you can get this diagnosis done. If you don't, then it's a problem. People will die within 48 hours. So what we believe is that in the end, with our Node-Pore sensing device, we will actually be able to, that people could use this in the ER and to diagnose it. So the number of markers that you need for APL is at least 5 or 6, and that's where we are right now. So, you know, I just like to always tell people, like, you know, this is a really nice project for the students, and my students are very motivated because they can see this real-world application and so forth. Right now, we're actually starting to screen patient samples from tissue banks, and we're going to see, you know, how well do we compare with the standards for diagnosing leukemia. We're also expanding to look at different types of cancers, and we're looking at circulating tumor cells because these are sort of sentinels. These are cells that live off of primary tumors in which they can circulate in the body, and some will actually lead to metastases. And 90% of cancer deaths are a result of metastases versus that primary tumor. We're also making a point-of-care system. We had this benchtop system with our preamps and so forth. Now we're down to just a small box that we can actually do our measurements in. So that's very nice. But overall, a general sort of sense of our technique and everything. How far can we go? How many markers can we screen? And remember at the beginning when I was talking about flow cytometry, state-of-the-art is up to 18 markers. You get a lot of problems with spectral overlap of the different fluorescents. We think we can go up to 10 at least at this point. And this is something that we're trying right now. And we think that we can actually be very competitive with what they call multicolor flow cytometry. So there's a lot of things to be done in this project right now. So with that, I just would like to end by sort of acknowledging my entire group, and in particular one of the groups, the MPS team as we call it, and really to my graduate student Karthik Balakrishnan, who's graduating hopefully in a few months, who really pushed this rod to actually look at multiple markers, and essentially my funding agency. So with that, thank you very much.
Okay, we have time for a few questions before the 5 o'clock break and the questioning period. Who wants to start? Scott.
So, I love seeing at the end the sort of bench top, and I imagine then you could have pre-designed plates that would then sample a set of markers, and you say this is the test one. My question was earlier when we were looking at this, and you were doing this on a statistical basis.
Yeah.
And then once you got the complicated set of markers, how well can you discriminate the signal you're going to get over? Do you get overlapping signals? How are you gating individual cells?
That's a great question. So it took us, again, this is where like statistics, we had to learn statistics. So are you talking about within the same device, the multiple? Okay, so I simplified it much more than really what's going on. But essentially, ideally, you're taking a cell and you're just comparing it to this control, right? But every cell will have a sort of these non-specific interactions. They're all different, right? So in the end, for this the data that I've shown you, we actually had a separate channel where everything was functionalized with the control antibody. So we ran a whole bunch of cells through so that we get sort of an average of how long did it take for, for these, or essentially what would be the average transit time for all these non-specific interactions.
So you have the anti
Yeah.
G1 in all 5 of those little spaces?
Exactly,
Okay.
exactly. So then, you'll notice this is a normalized transit time, so we actually take the transit time of each one of these subdivisions and divide it by this isotype control one, transit times. But then we actually end up, we compare it also, so actually this green line should be at 1. But the green line right now is above 1 because we actually take the IgG of all that in each different section and measure that average transit time. And this is including a 2 sigma deviation. So it's actually 1 plus 2 sigma. That sets our bar right here. So we've actually, the way to really do it, we realized afterwards, is we actually have to include another IgG right here so that we actually treat the IgG as its own, like, specific mark, almost like thing. So it's complicated.
So what would be, just a couple follow-ups, what would be the rate of cells going through this? And what are the, and what is a possible mechanism to let through one cell at a time?
Oh, another great question. So actually these cells, we're actually, the only thing that we do is we actually dilute the cells. So they're going through one at a time. Sometimes we do have multiple cells passing through, and it's very easy to see when the multiple cells pass through the channel because the current pulse has a very distinct signature, and we throw those out now. But actually, you can actually do sort of like a deconvolution. This is what we're working on, so that it doesn't matter how many you have in there. And that's something that I'm trying to get an undergrad to work out the algorithm to do that, because that will speed up our throughput.
So is it possible to run through the Node-Pore device a known colloid so you could match a signature with a known input? You build up like a library of...
You absolutely could do that. So we've actually done immunoassays where we actually, well, it was before Node-Pore existed, it would be a single channel, and essentially we do these sandwich assays of specific antibodies and everything. We can actually see the cells, the colloids actually be synthesized when there's a match. We actually, with the precision that we have in terms of size of a colloid, is down to a nanometer or so. That's how well we do everything. But then I always told my guys at the time, doing lots of light scattering, so why are we doing this? So that, that's sort of how the evolution of this whole project has come about.
How big is that little box? It looked like it was...
Oh, it's handheld. It's handheld, but we're actually also trying to get it down to a cell phone size. Everyone's all about the cell phone, but we thought we'd jump on that bad bargain too. So, yeah. More questions?
Yeah, I know you mentioned that they don't really care too much about the noise level, but imagine you have a collection of many different cells, with different sizes. Let's say you use this graph as an example. How do you really know one is a real peak, others are just noise or...
Yeah, so, and that's true, and so that's where we want to go to doing an FFT. And actually, it wouldn't be just, in this case, all the nodes are all equally spaced. But we would actually end up, we're also realizing that what we have to do is go through that picture that I showed you where some nodes are closely spaced versus some that are farther spaced. And that way, that helps us in terms of, again, extracting out the signal and out of the noise and everything.
Okay, and also one more question. How do you really decide what voltage you want to use?
Oh, yeah, that's a great question. So the voltage, the higher the voltage you go, you rise above the noise, so to speak. But you do get to a point where you actually end up going through electrolysis, and you'll get bubbles. You'll start to end up, it's a bad situation. So you just have to ramp it down, and so there's some complications in the measurement, but better than just injections, which are a little bit more hairy.
Okay, well, it's 5 o'clock, so let's thank our speaker and then I'll have our.